This is a recording of the first half of the 6.3 section. This particular recording will focus on binomial random variables. We've had a discussion that random variables are things that are both unpredictable in the short term and they produce numbers. Binomial random variables are a particular subset of discrete random variables that meet the binomial setting. The binomial setting has to meet these four criteria. For every single trial that we have, it's a series of trials, um, there's only two possible outcomes, which we will generally classify as success or failure. Each trial needs to be independent, meaning that earlier trials have no effect on future trials. There is a set number of trials, and then the probability of success on each trial is the same. If we meet the binomial setting and we count up the number of successes in the set number of trials, we have a binomial random variable. So a binomial random variable happens when we count the number of successes in a binomial setting. The probability distribution of that variable is called a binomial distribution, and the only parameters are n and p, meaning if you tell me the number of trials and the probability of success on each trial, then we know everything there is to know about that binomial setting. Let's take a look at some situations that may or may not be binomial settings. It says roll a die 10 times and let x be the number of sixes. Well, let's see if it meets the B criteria. Do we have success or failure? Yeah, success is considered getting a six, and failure is not getting a six. So it meets the binary setting. Is every trial independent? Well, we already know that rolls of dice are indeed independent, so they're independent. Is there a set number of trials? Yeah, the set number of trials is 10 because we're going to roll a die 10 times. And S, is the probability of success the same on every trial? Well, the answer to that is yes, because the probability is 1/6. So this fits the binomial setting. Okay. Observe the next 100 cars that go by and let C, the random variable, be the color. Do we have success or failure here? So are we binary? Um, I don't know what success is in this case. In the moment we fail one of the criteria, then the answer is no, this is not binomial. Okay. C, shoot a basketball 20 times from various locations in the court and let Y be the number of shots made. Well, are we binary? Yeah. Uh, Success is making the shot, and failure is otherwise. So we meet that criteria. Is every trial independent? Well, I'm not sure we can say that every single shot that you take with a basketball is independent. You learn a little bit of every shot. But for the sake of argument for this particular problem, we're going to say yes, independent, just for the sake of argument, that later shots are not influenced by earlier shots. So we'll say yes, independent for the sake of argument. And is there a set number of trials? Yeah. N is equal to 20. Same probability? Ah, this is where we fail. No, because probabilities change based on where you are in the court, based on your location. So it fails the same probability condition and therefore not binary. All right. Binary probabilities. We know we have this random variable, and we've been discussing about how to find the probability that the random variable takes on various values. uh, let's say each child in of a particular pair of parents has a 25% chance of having type O blood. Genetics say that children receive genes from their parents independently. If these parents have five children, count X the children with type O blood in this binomial variable situation. N equals 5 and probability of point of the probability of success on any individual trial is 0.25. Now, what's the probability of zero successes out of the five trials? Well, I'm going to write that down as it's essentially five failures in a row. And the probability of the first failure is 0.75 because the probability of success is 0.25. Probability of failure is 1 minus 2.5, which is 0.75. And the second and the third and the fourth and the fifth, each of them has probability 0.75 because they're all failures. So we could say that this probability is 0.75 to the fifth power, to the fifth power. So let's switch over to the calculator and do our calculations. Start a new document, open up a calculator, and we get 0.75 to the fifth power and 0.2373. 0.2373. Okay. Now, what's the probability of exactly one of the five children having type O blood? Well, let's think about having that one success. You could have a success um, and then followed by four failures. And the probability of that is the probability of that one success times the probability of those four failures, which ends up being 0.25 times 0.75 to the fourth power. And switching back over, 0.25 times 0.775 to the fourth. Okay, and that is 0.79, 0.0791. 0.0791. But another way that this could happen is that you could have a failure and then a success and then three failures. 0.75 times 0.25, 0.75 times 0.75 times 0.75. Well, that's just the same, 0.75 times 0.75 to the fourth. So that will also be 0.079. And if we go through the rest of these, um, failure, failure, success, failure, 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 success, failure, or failure, 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 success, all of them end up being 0.0791 each time. And how many of these did we have? We had one, two, three, four, five of them. So we could say that the probability of having exactly one success is is five times 0.0791, five times that number, and that gives us 0.3955. 0.3955. And similarly, we could have said that this is the probability of getting zero successes, and that was 0.2373. Great. How about having exactly two out of the five successes? Well, we could start with one way that could happen. Success, success, failure, 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 which is 0.25 times 0.25 times 0.75 times 0.75 times 0.75, or 0.25 squared times 0.75 cubed. Back to the calculator, 0.25 squared times 0.75 cubed. Okay, 0.0264. 0.0264. And I could continue on that route. Success, failure, success, failure, failure. But I think we could recognize that it will also be the 0.0264. Success, failure, failure, success, failure, success, failure, 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 success. Um, that's all the ones that start with one success. And then how about failure, success, success, failure, 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 success, failure, success, failure, failure, success, failure, failure, success, failure, uh, failure, success, success, failure, and failure, failure, success, failure, success, and the last one, failure, 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 success, success. One, two, three, four, five, six, seven, eight, nine, 10 of them. So we may think of the probability of having exactly two successes is this number 10, because there's 10 different ways to have two successes out of five tries, multiplied by the 0.0264, and that ends up being 2640. All right. Um, and that is one way to do this. But the fact that, we had 10 or 5, or in this case, we could think of this as multiplied by 1 because there's only one way to have all failures. We could try to take this idea and make it more real. And we're going to talk about that number that we multiplied by being called the binomial coefficient. And the binomial coefficient is a way to find out that number of ways, without having to have enumerated all the different things. We say that number is pronounced um, uh, n choose k. In the first example, it was 5 choose 0, which was equal to 1. In the second example, it was 5 choose 1, which ended up being 5. And in the third example, it was 5 choose 2, which was 10. Now, let's take this 10 for example. We could use this formula and say, oh, 5 choose 2. Well, that's the top number 5 factorial. And 5 factorial is 5 times 4 times 3 times 2, 2 times 1. And you divide it by k factorial, which is the lower number. And factorial is 2 times 1. And then n minus k factorial. Well, n is 5, k is 2. So n minus k factorial is 3 factorial, which is 3 times 2 times 1. And you see that these 3's, 2's, and 1's cancel. This 2 cancels it with this 4. And indeed, you get 5 times 2, which is 10. And that's one way to find the binomial coefficient. Another way, um, which you may have seen in another class, is something called Pascal's triangle. Um, this is where each successive row is found by adding the values of the terms above it. So 1 plus 3 is 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And that 10 that we just found is that one. The 5, that was 5 choose 1, is that one. And the 1, which was 5 choose 0, is that one. And that's another way to find the value of this coefficient. All right? So as we said before, 5 choose 2. 5 times 4 times 3 times 2 times 1 over this. And as we saw before, that reduces down to 10. Okay. And again, we pronounce that 5 choose 2. That number, that binomial coefficient, is that number that says this is the number of arrangements of k successes and n tries. And then this part was the numerical part, like the 0.25 cubed times 0.75 squared, because we had 3 successes and 2 failures. And that's how we calculate the binomial probability. So going on, what's the probability of exactly 3 um, children having type O blood? Well, that is going to be the probability of x equals 3 is going to be 5 choose 3 times 0.25 cubed times 0.75 squared using that previous formula. And I think you saw from Pascal's triangle that this 5 choose 3 is the actual number 10. So 10 times 0.25 cubed, 0.75 squared. 10 times 0.25 cubed times 0.75 squared. And there's 8 0.087. That's wrong, that's a 9. Um, 0.089. There we go. Now, would you be surprised if more than 3 children have type O blood? Well, one way to answer that question, what's the probability of x being greater than 3? We could think of it as the probability of x being exactly 4 plus the probability of x being exactly 5. Or we could think of this as 1 minus the probability of exactly 1 plus the probability of exactly 2 plus the probability of exactly 3. And we've already calculated those numbers. So that is 1 minus, here's the probability of, I'm sorry, put in a parenthesis first, 1 minus this probability and that probability, which I screwed up. I'm going to put a plus sign in here, right here. And then one more probability, and that's the probability of 0 successes. And look at that. And I'm missing something here. Plus the probability of exactly 0, forgot that one. And this is 1 minus the last one we calculated. Well, this one is the 0.0879. The time before that, if I go back in time, um, that is probability of exactly 2 was 0.26. sorry, yep, 0.2640. Exactly one was 0.3955. And then that last one, 0.2373. All right. And ignore this miss up from the time before. One minus the sum of those. And I'll do them in order 0.273 plus 0.3955 plus 0.2640 plus um, 0.0879. There we go. And that probability ends up being about 1.5%. Okay. And we would be surprised. And why would we be surprised? Because this probability of more than three is less than 0.05, which is our arbitrary number for being surprised. All right. So let's take a look at another problem. So suppose you came in for class today unprepared for a quiz. You didn't read the text, you didn't do the practice problems, you didn't take any notes, you didn't answer any questions in class. The quiz consists of 10 multiple choice questions. Since you are completely unprepared, you decide to randomly fill in the answers on your bubble sheet without even reading the questions. Let X be the number of correct. Can we confirm that this is binomial? Well, let's see. B for binary. Are we binary? Binary. And the answer is each trial ends in success or failure. Either you got the either you got the answer right or you got it wrong. So yep, success or failure. Independent, and say that each of these trials are indeed independent because earlier successes or failures don't affect future ones. So we're independent. Is there set number of trials? Yeah, the n in this case is 10. Is the bins, S, is it the same probability for each trial? And in this case, let's say this is our same test that we take, and there's 5 options. Probability in this case would indeed be 0.2 for every single trial. So yes, binary. All right. So find the probability of getting exactly 3 correct. Probability of this is 10 choose 3 times 0.2 cubed times 0.8 to the 7th. Because the probability of getting them right is 0.2, and we're getting 3 right. Probability of getting a failure is 0.8, and doing that 7 times. Um, now, is time for, say, 7 choose 3. Mm, 7 choose 3. That's like 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 factorial, which is 3 times 2 times 1, times 10 minus 3 factorial, which is 7 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1. And then we could say, well, all of these cross off with all of those. This 3 and that 9 reduce, this 2 and this 8 reduce. So it looks like that number is 120. 120 times zero point 0.2 cubed times zero point 0.8 to the seventh. Now, we did all that work, but it's now probably time to show you an easier way of getting that 120, right? And that is under on our calculator, under menu, under probability, there's an option called combinations. And if I hit 10 comma 3, there's that same 120 with a lot less work. So maybe we say 120 times zero point 0.2 to the third times zero point 0.8 to the seventh, and there's our probability, 2013. All right. And what does this mean? What does this result mean? Um, there is a 20.13% chance of getting exactly 3 questions correct. Okay. Um, During a passing score, a student must guess correctly 6 times. Would you be surprised of earning a passing score? Compute the appropriate probability to support your answer. Well, what are we asking for? We're asking for the probability of the number of answers correct being greater than or equal to 6. Now, I could break this problem down into probability of getting 6 or exactly 7 or exactly 8 or exactly 9 or exactly 10 questions correct. But I think what we'll say is that's a lot of work, and maybe it's time to take a look at more technology that would make this problem a little bit easier. Okay, first of all, could I calculate the probability of getting exactly 6 right by hand? I could, okay, but I'm going to introduce a new idea, and that is something called the binomial PDF function. And the binomial PDF function will give to us the probability of some exact outcome in a binomial situation. So going here, I could go to probability, distributions, and then way down here, we've got binomial PDF. If I choose that, it asks for me how many trials, probability of success, and what value am I looking for? And then looking for exactly 6 successes, and that ends up being 0.005505. So I could put that in 0.00505. So pretty unlikely that that would happen. And I could do this again and just say 7. And now I got 0.000786. 0.000786. And I could do that for all of these. But even that is a lot of work. So there's a third command that I want to expose you to on the calculator, and that's the binomial CDF, where we can combine outcomes that we're looking for. So in the case of I want 6 or more successes, that would be, again, this is under probability distributions, and it's at the bottom here. Binomial CDF. You could say, well, 10 trials, yes. Probability of success is 0.2. My lower bound, what's the lowest number of acceptable um, successes? 6. Upper bound is 10. And this will add up all of those probabilities. And when we do that, we get 0.006369. All right. And again, that's using the command binom CDF 10 trials, 0.2610. And with all calculator code, this is number of trials, that document. This is probability. This is our lower bound, and this is our upper bound. And you can see we do that. So the commands, again, that we learned about, and that is NCR for calculating um, the binomial coefficient, PDF if you're looking for some exact outcome, or CDF if you're looking for some range of outcomes. So in the case of the 5 children in type O blood, if we want to know exactly 3 children with type O blood, would type in PDF C 5 comma 2.5 times 3. Let's get that out of the way. Menu, probability, distributions, and that's binomial PDF, which is A. 5 trials, 0.25 chance of success, 3 successes, and you get 0.079, 0.0879. If you're looking for more than 3, then lower would use a CDF, lower bound 4, upper bound 5. And again, that's under menu, probability, distributions, and this should be option B for the CDF. Number of trials, 5, probability of success, 0.25. Lower bound was 4, upper bound was 5. And there's that same 0.015, 0.0156. Okay. And of course, if you wanted to calculate these by individuals, you could have calculated the PDFs of these individuals by hand and added them up. Let's take a quick look at what that looks like. Menu, probability, distributions. That's the PDF, 10, sorry, 5 trials, 0.25, 4, and we're going to add to that menu, probability, distributions, binomial PDF, 5, 5, and 5. And you can see that that number here is exactly the same number that we got out of the CDF function. All right. And that's a good place to end this recording.